Welcome to Adaptive Computing's booth. Feel free to come in and have a seat. Joining us today on the stage is Jenett Tillotson with Indiana University. She's going to talk about fair share in Moab. All right, thank you.
All right, thank you. All right, hi, I'm Jenett Tillotson from Indiana University. I'm a senior cluster system administrator there, and we have several, so I have to make sure I do this right. Oh, good. So we have several clusters at Indiana University, and today I'm going to talk about how we use Moab to fairly share these machines. So we have Big Red, which is a 1024 node blade center. It's all PowerPC. And then we have Quarry, which is our x86 system. It's also half blade center and half iDataplex. And there's about 400 nodes between the two halves. And then we have Mason, which is an HP large memory system. 16 nodes with 512 gigabytes of memory per node. And we use Moab on all these to fairly share them among all the researchers at Indiana University. So at IU, the computing resources are treated like the library. So they're free to all researchers, shared equally among our researchers, so no one researcher is privileged over another. So in order to do that, we have to do some things on our clusters. So here you can see by logins, how many logins we have on the machine. We have logins across all the departments of the university. Of course, mostly physics, informatics, chemistry. Those are our big users. But we also have people in political science that use our clusters, people in business that use our clusters. So because of this free and open nature of our clusters, we get a large range of researchers using them. But as you can see here, like informatics is the largest user of our cluster by job. So they run the most on our cluster, but still we get people in economics, in anthropology, psychology. So this open nature allows anybody to use the resources. So we have our queuing system. We have a long queue that generally gets you more nodes or fewer nodes for longer days. So in this case, like on Big Red, it'll get you 32 nodes for 2 weeks. And then we have a normal queue, which will get you more nodes, like 256 nodes, but it'll only get you for a couple of days. And we use that partitioning to keep resources available for large jobs, but then allow smaller jobs that need longer time to run as well. And then we have a serial queue where you can run individual jobs. And we do have quite a few users that run thousands, tens of thousands of jobs a month through our queuing systems. Good. So in order to fairly use this machine, the thing we use the most is fair share. I can tell you most of what we do for prioritization is fair share. Fair share is by far the easiest thing to make sure that the cluster is accessible by all researchers and that no one researcher can take the machine over from another researcher. So we try to give every user, we have about 300 active users on the machine at any given time, and we give each user 5% of the cluster. So that just means until they've used 5% of the cluster, they're equal, on an equal footing with everyone else. But once they use 5%, their priority starts to go down, and their jobs will move down in the queue. And that allows researchers who are coming onto the machine for the first time to get quicker access to the machine. But researchers that have been using it for a while, over the last few weeks, to then get pushed down in the queues. And it's by far the most useful option in Moab. The other thing we do is we look at X factor. So X factor is a ratio of how long the job has been waiting in the queue versus how long it's going to run. So you don't want a job that's only going to run for an hour to wait for a month in the queue. So this ratio looks at the X factor looks at a ratio of that, and if the job is starting to wait much longer than it's going to run, its priority will start to go up, and those jobs will move up in the queues. And the other thing is queue time. So that, as you can see, this is what Moab puts out when you look at priority, and you can see that queue time is the other thing. So the longer a job's been waiting in the queue, the higher its priority will be. So jobs that come in later in the queue will tend to be lower in the queue than jobs that come in earlier in the queue. So the other thing we do to increase utilization, we also put limits on our users, right, to make sure that they don't take over the cluster. So one of the things that users can do is they can do queue stuffing. So what they'll do is they'll submit many jobs into the queue, like hundreds or thousands of jobs, and that means since they'll accrue priority based on how long they've been in the queue, those jobs then can take over the queues. and one user can start to run more jobs than others. So what we do is we block the jobs, and we only allow 16 jobs in the idle queue at a time. So only 16 jobs are accruing priority based on wait time. The rest of the jobs are blocked until they move into the idle queue, and then they accrue wait time. So this keeps one user from being able to stuff the queues and allows everybody to have their 16 jobs in the idle queue that are waiting to be run. And so that helps prevent starvation, so that one user can't take over the entire cluster. The other thing we do is we do limit nodes per user in the queue, so one user can only have a certain number of queues total, or number of nodes total in any given queue, so they can run more long jobs. In the queue they can run 3 or 4 long jobs, but once they've reached a maximum number of nodes that all their jobs are running on, they'll be blocked as well. And they also limit the number of jobs that can be submitted total to the resource manager by any one user. Mostly that's just to keep the resource manager from being overwhelmed. So if you can see, like when people have 100,000 jobs to run in the queues, we don't want them to submit all 100,000 jobs all at the same time, because the resource manager just can't keep track of that many jobs. So those are the limits we put on our users. And then the other thing we do to improve utilization is we use the QoS facility rather than reservations. So every once in a while we'll have a researcher that comes to us, really needs a certain number of nodes because he's got a paper he's writing, or she's got a grant that's due soon. And so what we do, instead of reserving them nodes so that they can run jobs and get data results quickly, what we do instead is we give them a QoS. And what that does is that'll bump their priority up in the queue and give what we call next to run status. So their jobs will come to the top of the queues until they are running on a certain number of nodes. And then they lose that priority bump and they become like any other user. In fact, their jobs will be blocked at that point. So what that means is the QoS it's not tied to any particular resource on the cluster. So normally with a reservation you say these nodes 1 through 10 are reserved for this user, but instead I can just say the next 10 nodes that are available are for this user. So once those nodes become available, the user can get them, and then as long as they keep jobs in the queue, they'll keep those nodes so they can continue to run until they get all the jobs they need through the queues. So the idea of the QoS, before when we were using reservations to do this, those nodes, when the user wasn't using them, they were reserved for, they would remain idle. And we would lower our utilization on the cluster. But with the QoS, where that can float among any nodes, and if the user doesn't submit jobs, those nodes that they were using could be used by other researchers. Until they put jobs in the queue, then they get a priority bump, and then they get the next 10 nodes in the cluster. So as long as they keep jobs in the queue, they keep that set of nodes, and if they fail to submit them, then those resources that normally would be reserved and held for the researcher can be used by other people. So again, like the library, if the book's not checked out, you get to check it out. And then the other thing that we do with Moab is we have this Mason cluster that I mentioned. It's a 16-node cluster. 12 of the nodes are used for genomics research, and the other 4 nodes are for general IU, Indiana University researcher use. And these are large memory nodes, so they have 512 gigabytes per node. So what we want to do is, the genomics people, they need large amounts of memory, 256 gigabytes of memory per job, but they don't necessarily need a lot of cores. So what we really want to do is we want to schedule this cluster by memory rather than by cores. So in this case what we do is in the submit filter in Torque, we use the submit filter to force the users to choose a vMemory. So by forcing them to pick vmem in their job script, when their job runs, Torque will then set a U-limit on their process. So that means the user can't go outside of that. So if they ask for 256 gigs of memory, for the most part, then they are limited to 256 gigs of memory, and if they try to allocate more, ask for more memory, they'll be limited by the operating system. It'll tell them they can't allocate any more memory. And this allows us to break the node up by memory rather than by core. And then we're not currently using a group fair share. Right now we're just letting jobs run. It's a fairly new cluster, but at some point we're going to eventually make it so that there's a group fair share, so that as soon as 4 nodes are being used, or the equivalent of 4 nodes of memory are being used by IU researchers, then no IU researchers can get any more nodes running, or any more jobs running on Mason. And likewise for the genomics people, the same idea. So we can do like a 75%, 25% split of the cluster between the two different kinds of users. So that's basically how we use Moab at IU. So does anybody have any questions? No? Yes? Yeah, so IU, the newest thing is that IU is buying a new supercomputer. We're buying a petaflop Cray. It'll be, see if I got this right, 767 nodes. Do you know the exact which one? 767 nodes of, I think, CPU, GPU nodes, and then 344 nodes. It's one way or the other. It's 344 nodes of one and 676 of the other, but it'll be a hybrid CPU, GPU Cray. Yep, and we'll run Moab on that as well. It'll be very interesting. It's a new foray for me. So, but we just announced that a couple weeks ago, and we'll be taking that machine over. They'll be delivered, I think, in March is when we'll get that machine. Yeah. Yes. I'm sorry. Who runs it?
Who funds the Big Red?
Oh, who funds it? Some of the clusters have been funded by grants. So Big Red, half of Big Red was funded by a Lilly Foundation grant, Lilly being the big drug manufacturer in Indiana. And then the other half of Big Red was actually donated to us by IBM. But the rest of the resources are purchased by the university. So the university really does treat these systems like they treat the library. So they're centralized resources available to everyone. Literally, on our systems, if you're an IU faculty member, you go to a website, click a button, hit another button, and you've got an account in 15 minutes, and you can be running right away. So really it's treated like the library, and all funded by the university. So the Cray was all university money. Yep. Yeah, and it's named Big Red 2, by the way. That is the right name. What? Run Moab? Yes, we're going to run Moab and Torque. Yep. Yep. Any other questions? All right, good. All right, thank you.